In this video, we'll be talking about Planck's black body radiation law. But before going into Planck's black body radiation law, it's quite important that we must talk about the the background of this problem. And the background of this problem is that if we have a black body, I mean a body which can absorb radiations and can emit radiations equal to 100%. Ideally, this is what's called as the black body. So anybody which is capable of absorbing all wavelengths or all frequencies and the reverse. So if we assume that we have a black body which is close to a black body, because we cannot have uh, a body which can absorb 100% of radiations. So if we have a situation like this, what we obtain when we perform some experiment on the radiations that are emitted or absorbed. Now, if this axis is about the wavelength and this is the energy, what we observe the curves like this. I may call this as T1, T2, and T3. So we have three curves having different range of temperatures. And we can see that the maximum value of lambda, it shifts. Oh no, here it should have been more like this. So this is, say, lambda 1, lambda 2, and lambda 3. Now, what is observed? I mean, we have some experimental setup where we can draw the curve between the wavelength of the radiation and the energy. Now, what is observed? What is observed in these curves? So this is the wrong part of the curve T3. Okay. So what is observed is that the energy is not uniformly distributed in the radiation spectrum. We can see there's variation of energy. And and at the given temperature, if we look, for example, at temperature T1, the intensity of radiation increases. It increases with increase of the wavelength and becomes maximum at some particular lambda. And on further increasing the wavelength of the radiation, there is a fall. There's a fall in the intensity of the heat radiations. The next important thing is that this increase in the temperature, what it causes basically, what we have here is that this T3 is greater than T2 is greater than T1. So if we look for T2 here, what we observe is that this on increasing the temperature, the value of this lambda, I think the better will be to call it lambda 1 max, lambda 2 max, and lambda 3 max. So what is happening to the value of this maximum wavelength? It's shifting towards the left. And this lambda m t, it comes out to be a constant. And this constant, as calculated in the original experiment, is 0.2896 centimeter Kelvin. So this lambda m is the wavelength for which the energy emitted is maximum. And this relation that we have here, what we call this relation, is called as Wayne's law. And we may call it Wayne's displacement law as well. Now, an increase in the temperature causes in increase in the emission of energy. So we can see that the T1 is less than that of T2 is less than that of T3. So if we look at the magnitude of energy that's being emitted uh, is more when the temperature is more. And the area, if we calculate this area under this curve, say if I calculate this area for T1, this area under the curve basically represents uh, it represents the total energy emitted. So it gives us the measure of the total energy uh, emitted, and at a particular temperature for the range of wavelengths. So wavelengths are going on, and if we measure this area under this curve, it gives us what it gives us is that this energy is found to be directly proportional. So measure the area, you'll get the energy, and this energy is found proportional to the fourth power of temperature. So I can say here that I can directly interpret it like that the area that's enclosed by the curves for the particular temperature is directly proportional to the fourth power of the temperature. And this equation is our Stephen's law. So what we call it Stephen's law. So moving on from here, what we have is Rayleigh-Jean's law. So Rayleigh-Jean's law. So what they tried to use the classical theory of physics to explain this spectrum, to explain this this range of energies that are emitted by a black body. So Rayleigh and Jeans, what they did, they tried to derive an expression for the radiation per unit volume uh, of a hot body in a frequency range of nu and d nu. And in their derivation, what they supposed, I mean, in their derivation of radiation law, it was assumed that the radiation is broken up. It's broken up into monochromatic wave trains. Monochromatic wave trains. And the number of such trains or equivalent degree of freedom lying between the frequency range of nu and nu plus d nu was determined. And then the energy carried by each degree of freedom is calculated, and it's calculated from general statistical theory, and hence the energy density of the radiation can be determined. So we'll not go into actual details of Rayleigh and Jeans because our motivation is basically Planck's black body radiation law. So what Rayleigh and Jeans found, and they found the number of independent vibrations or degree of freedom or degree of freedom per unit volume with frequency range of nu and nu plus d nu equals to 8 pi nu square d nu by c cube. And the the energy associated with each degree of freedom, I mean, according to Maxwell-Boltzmann's equation, so according to Maxwell-Boltzmann's law, the energy associated with each degree of freedom can be written as, and this energy can be written, say it is E, and can be written as adding up all the energies e to the power of minus E by kt dE by integral 0 to infinity e to the power of minus E by kt and dE. So on calculating this for 1 degree of freedom, what we get is kt. So this is the average energy. So thus, according to classical theory, the average energy associated with each degree of freedom is kT, and that's the energy per unit volume in the frequency range of nu, and nu plus p nu can be written as E nu. So can be written as E nu. D nu is 8 pi nu square d nu by c cube kT. Now, this equation is what is called as Rayleigh-Jean's radiation law. And this equation is derived purely from classical assumptions, classical postulates, classical, uh, classical laws. Now, according to this expression, what does this expression tell us is that the energy emitted by the black body, it simply increases with the increase in the frequency and becomes infinite at large frequencies. And if we go back to the experimental observation, what was that? If I trace down the experimentally calculated, measured the spectrum in terms of the frequency, it looks like this. If I choose this as nu and the y-axis as E nu, so the curve is something like this. But uh, but according to the result that we have obtained here, what it is telling us is that the frequency is infinite, the energy emitted is infinite. And the experimentally observed radiation curve is in complete disagreement with the equation that is obtained by Rayleigh and Jeans. So there is a complete disagreement between the theoretically predicted equation and the experimentally observed curve. And what this disagreement with this conclusion, I mean, since the experimental curve shows that the energy radiated at a particular temperature becomes zero, both at lower uh, as well as higher frequencies. So it goes to low, very very low. At higher at low as well as higher frequencies. So there is a complete disagreement. I mean, if we plot Rayleigh-Jean's law, its outcome will come something like this. Now, at the same time, if we calculate the energy carried out by all frequencies, so if I have to write E, I can write down it as the integration of E nu d nu. So this is going to be integration from 0 to infinity, 8 pi nu square kT d nu by c cube. Now, the value of this integral is infinity for any value of t. For any value of t, the value of this integral is 0. And this physically means that the total energy emitted by the black body per unit area, per unit time is infinite. It is infinite at all temperatures. And certainly this is completely a false conclusion. And both the conclusions that we talked about here, they are incorrect, and they fail completely to account for the observed spectrum of radiation emitted by a black body. And the frequency distribution of the black body could not be explained on the basis of the classical concept, in spite of repeated repeated attempts by various scientists around the globe. And this discrepancy in classical calculations and the facts that were observed experimentally, and this discrepancy was removed basically by Max Planck, and and Max Planck removed this discrepancy by introducing the quantum theory, by introducing the quantum concept to explain this black body radiation law. Now, moving on to Planck's black body radiation law. Now, what were the basic assumptions of Max Planck to explain the observed experimental curve that I showed you right now? What was that? What Planck did basically, Planck found an empirical formula to explain the experimentally observed distribution of energy. So the distribution of energy is certainly something like this. This is nu and this is E nu. And the formula uh, uh, that Max Planck achieved, uh, it can be achieved by making use of the what we call as Planck's hypothesis, and there were some important assumptions in obtaining an equation to describe the experimentally observed radiation spectrum. The very first important point is that a black body radiation chamber, if we have a black body, uh, uh, if we have a black body, its radiation chamber is filled up not only with radiations but also with simple harmonic oscillators, or you may call them resonators of molecular dimensions, which we call as Planck's oscillators. Or resonators, and these oscillators can vibrate. They can vibrate with all possible they can vibrate with all possible frequencies. The vibration of the resonator that we have, uh, uh, that's associated with 1 degree of freedom only. So if we have an oscillator and this oscillator is vibrating, it is oscillating with 1 degree of freedom. The next important point is that the oscillators, or we may call them resonators, they can radiate energy, they can emit energy, they can absorb energy. They can radiate them, they can absorb energy continuously. But an oscillator of frequency, say nu, can only radiate or absorb energy in the units. Uh, they can absorb energy in the units or quantas of magnitude h nu, where this h is called Planck's constant. And this h is basically a universal constant, and we call this as the Planck's constant, and its value is known to us, and its value is we can write down its value is 6.6 times 10 to the power of minus 34 joule second. Now this assumption is the most revolutionary in character. It's uh, I mean, at the same time, if I had to translate this thing in other words, what it means is that, what it states is that the exchange of energy between the radiation and matter, exchange of energy between radiation and matter cannot take place continuously, but they are limited to discrete set of values. And these discrete set of values can start from 0 to h nu, 2 h nu, and so on so forth to n h nu. In the multiples of some small unit, what we have here as h nu. And now, in order to derive this Planck's radiation law, what is important here is that we first we try to obtain the number of resonators per unit volume that are lying in some frequency range. So we'll be looking for number of these oscillators or resonators in the frequency range of nu and nu plus d nu. So to start with, I mean, the number of modes of vibration per unit volume within this frequency range, that is equal to 4 pi nu square d nu by c cube. Now, the black body radiation, what is happening here is that the radiation travel with the speed equal to the speed of light, and they are transverse in nature, and Yeah. And if they are not like that of longitudinal waves, what we call as sound waves in the string, which are longitudinal. So what goes important here is that as we have two kinds of possibilities here, we can have, as there are two possible polarization states, transverse for each transverse wave, the number of modes of the vibration of these transverse wave is doubled. It's double as for the longitudinal waves. So for black body radiations or electromagnetic waves, the number of modes of vibration per unit volume within this frequency range is 2 times the number of resonators that we have. Now let's calculate the average energy of this Planck's oscillator. Now, if I assume that I have n as the total number of total number of Planck's oscillators or resonators. So assuming that we have n total number of Planck's oscillators, and E is their total energy. E is their total energy. It's the total energy. Then the average energy per Planck's oscillator, if I represent that energy by E bar, this average energy per Planck's oscillator will be E by N. There should be no doubt about this. So this E bar is a representative of what? It's a representative of the average energy per Planck oscillator. So moving from here, now let's apply the Maxwell's law of molecular motion. Now what Maxwell's law of molecular motion states that if we have some say epsilon is a certain amount of energy, the probability that a system will have energy is 0, epsilon, twice epsilon, dash 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 to say some k epsilon. They will be in the ratio of 1 is to e to the power of minus epsilon by kt, is to e to the power of minus k epsilon by kt. Okay, I have Boltzmann here. Let me use something else. Let's suppose this is r. So this is r epsilon by kt, and so on and so forth. Now, if I assume that N0 is the number of resonators that have energy equal to 0. I mean, they have 0 energy. Then the number of resonators N1, they have the energy equal to epsilon. And then what will be the number of the number N1 of resonators whose energy is epsilon? Their number will be N0 e to the power of minus epsilon by kt. And the number of resonators N2 having the energy twice epsilon, what they will have, N0 e to the power of minus twice epsilon by kt. And we can generalize this thing into a number of resonators, and we can move this up to nr, having energy Re. So how will this go? This can go, then I can write down n equals n0 plus n1 plus n2 plus so on and so forth to some nr plus so on and so forth. So I can use the values. So this is n0 plus, this is n0 e to the power of minus epsilon by kt, plus n0 e to the power of minus twice epsilon by kt. And this will go on and on. And I can have n0 out. So inside I'll be left with 1 plus, let me say x, plus x squared plus so on and so forth. So I have substituted x for what? So what should be x? X is e to the power of minus epsilon by kt. Okay, and so what will be our result is n will be equal to n0 times 1 plus x squared plus so on and so forth. And this series can be approximated as 1 plus x squared plus so on and so forth. This is equal to 1 by 1 minus x. So we can have here n equal to n0 by 1 minus x. So this I will call as equation 1. Now, talking about the total energy of Planck's oscillators. So how can we write down the total energy? Total energy of Planck's oscillators, or you may call them resonators. I have very bad handwriting. I can't do anything with it. So for that, I can write down E as having zero energy times n0 plus having energy E is n1, having energy twice epsilon, I'm calling it epsilon, n2, and so on and so forth. This will go like this. So we can look for epsilon n1. Instead of n1, we'll go with n0 e to the power of twice epsilon by kt, plus we will have twice epsilon and 0 e to the power of minus twice epsilon by kt, and plus so on and so forth. So we can write down n0 can be out, epsilon can be out. So what we'll be left with is I think here it should be minus epsilon. So we'll be left with e to the power of minus epsilon by kt, and then plus twice e to the power of minus twice epsilon by kt, and then plus so on and so forth. So we can write down this as n0 epsilon times x plus x squared, twice x squared, plus so on and so forth. So we'll go on like this, and let me use this. If I do it like this, that this is my my s. I'll call this something like, say, s. Okay. Now, so this is my s. No, I'll not. This is my e. Let me go with e. So I call this as s. I'll call this as s is what? S is x plus twice x squared plus so on and so forth. This will go on like this. I'll multiply this with x, so sx will be it will be x squared plus 2x cubed plus so on and so forth. So I will subtract the two. If I'll call this A, I'll call this B. I'll subtract these two. So this is my standing equation. I'll call this 3. If I subtract these two equations, what will I get? I will get S minus Sy is equal to Y plus Y squared plus so on and so forth. And I can have S out. So this is 1 minus y is. So this is over. Why am I writing y here? This is in terms of x. So 1 minus x. So this is x, and this is x squared plus so on and so forth. So this is x plus x squared plus so on and so forth. So this is already obtained. So what will be s will be, what is this? This is 1 by 1 minus x. Divide by 1 minus x. So this is going to be 1 by 1 minus x whole square. Now if I use this, so I have evaluated this thing, I can use it here. So E will be n0 epsilon. So E will be n0 epsilon by 1 minus x whole square. So this should be my equation number 4. Okay, so I have missed something here, I think. Yeah, so this is x. So no, here it is x by. So x plus x squared plus so on and so forth. This series will give me x by 1 minus x. So 1 minus x will come from here. So we will have x by 1 minus x whole square. So that should be the case here. So this will be E. So I can calculate now average energy. So I can calculate the average energy now. So what will be average energy? So average energy of the resonator, average energy of the oscillator. So that average energy I'll call E bar. So that will be simply, as I defined that at the very first, that will be E by N. So what will be this E bar? So E is already calculated as N0. Here it is X. Okay, it's N0. Why am I writing 0 here? It's N0 X epsilon. This is N0 X epsilon by 1 minus X whole square. So divide by N, so that will multiply. What was that? What was that? Okay, so what is N is N0, so N, so 1 minus X will go up, divide by N0. This N0 and N0 will cancel, the square and this thing will cancel, so I got average energy of the oscillator. That will be X epsilon by 1 minus X. But what was X assumed to be? X was, what was X? X was e to the power of minus epsilon by kt. This was X. So I can use the value of X in this equation to calculate this average energy per oscillator. So I can write this E bar, which is the average energy, that will be e to the power of minus epsilon by kt. Then I have epsilon divided by 1 minus e to the power of minus epsilon by kt. All right, I can multiply and divide by e to the power of epsilon by kt. So what will I get? E bar will be epsilon. So this will give me 1 divided by e to the power of epsilon by kt minus 1. Now, according to the hypothesis of Max Planck, according to the Planck's hypothesis of quantum theory, this epsilon is h nu. So I can say that the average energy of the Planck's oscillator, so average energy of Planck's oscillator, that is epsilon bar, is going to be, it is going to be h nu by e to the power of h nu by kt minus 1. Now, so this is the average energy. This is the average energy of the Planck's oscillator. Now, the energy density belonging to the range. So we are talking about the energy density over a range, and that range is what? That's d nu. That's between nu and nu plus d nu. And that range can be obtained by multiplying this average energy that we have. Let me call it E nu now. E nu d nu. That will be what? That will be 8 pi nu square by c cube d nu times h nu by e to the power of h nu by kt minus 1. So what am I trying to say here is that the energy density that belongs to the frequency range of nu and nu plus d nu. This can be obtained by multiplying the average energy of the Planck's oscillator by the number of the oscillators per unit volume within the frequency range of nu and nu plus d nu. So what we will have is, what we have basically is the Planck's black body radiation. E nu d nu is, I can write down 8 pi nu cube by c cube times 1 by e to the power of h nu by kt minus 1 d nu. So this equation gives me the energy density. I mean, the total energy per unit volume belonging to the frequency range of nu and nu plus d nu. And we can translate this Planck's black body radiation law in terms of wavelength also. So if we have to translate this equation in terms of the wavelengths, we can write down nu is c by lambda. So what will d nu be? That will be minus c by lambda square. So let me take the magnitude of d nu will be c by lambda square d lambda. So it will be like this. So we'll be using those things into this equation, and we can obtain the Planck's blackbody radiation law equation in terms of wavelength. So doing so, what we'll get E lambda d lambda. So that will be 8 pi h by c cube times c cube by lambda cube times 1 by e to the power of hc by lambda kt minus 1. And then for d nu, what we will use is c by lambda, because we'll be using only the magnitude d lambda. So we will have the final equation 8 pi h by c cube, and c cube will go. So lambda cube will give me lambda raised power 5. D lambda will be on the top. E to the power of hc by lambda kt minus 1. So this is our Planck's equation in terms of the wave, in terms of the wavelength, and the result that we have obtained here is very much consistent. It's consistent with it is consistent with what is experimentally obtained. So if I have to roughly estimate this equation, I can think of a graph like this, and if I have this lambda in terms of say micrometers, say mu, and this is E lambda d lambda. So this is our theoretical curve, and these are our experimental points. So we can see that the, the the theoretical predictions of the Planck's blackbody radiation law, they are very much consistent with what is experimentally obtained here for wavelength. And if we have to plot Rayleigh-Jean's law for this experimental curve, that law will certainly go like this. So this is your Rayleigh-Jean's law curve. So we can see that the theoretically predicted results are very much they're very much close to what is experimentally obtained here. So that's what makes this equation so powerful, because it was able to explain the energy density spectrum of a black body. And we can certainly move on from here. I mean, we can boil down this Planck's blackbody radiation law under certain mathematical limits, where we can achieve the results that were predicted by the classical predictions. So in doing so, we can do that. And suppose if I move from here, so this is my Planck's blackbody radiation law, and I can write down this again. This is E lambda d lambda is 8 pi h by lambda raised power 5 d lambda by e to the power of hc by lambda kt minus 1. All right. So in the limit of this e to the power of hc by lambda kt very greater than 1, we have E lambda d lambda will be 8 pi h by lambda raised power 5 e to the power of minus hc by lambda kt d lambda. So this is nothing but Wien's law. This is Wien's law. And at the same time, for longer wavelengths, so here we are assuming that the wavelength is small, so that the exponential term is large. But if we take the reverse, if we take for longer wavelength, I mean for longer lambda, so this e to the power of hc by lambda kt, it can be approximated to 1 plus hc by lambda kt. So we can use this thing in our Planck's blackbody radiation law, and what we'll obtain? We will obtain E lambda d lambda will be 8 pi hc by lambda raised power 5, 1 by 1 plus hc by lambda kt minus 1. I think this minus 1 and plus 1 will cancel. Now this will go up, so 1 lambda, and this will convert to 4, and we'll boil down this to 8 pi hc. Kt will go up, divide by lambda raised power 4 d lambda. Now you can convert this in terms of frequency, and you will see that you are back to what's called as Rayleigh-Jeans law. So this is our Rayleigh-Jeans law. So what we see here is that Wayne's law, uh, it holds for shorter wavelengths, and Rayleigh-Jeans law, it holds for longer wavelengths. So at this point we can say that both the Wayne's law and Rayleigh-Jeans law, they are basically incorporated in the Planck's blackbody radiation law. Or in other words, we can say they are the limitations. Under certain limits, the Planck's law boils down to Wayne's law and Rayleigh-Jeans law.